Okay, it's time now to take a look at integration, which is, as I've said in my note here, also known as anti-differentiation. And I guess as its name suggests, is the reverse process to differentiation. So, and it has uses in motion, area, and volume. So when we differentiate, so if we derive, let's derive a function x squared plus 2x. The derivative of x squared plus 2x is equal to 2x plus 2. Okay, so going in this direction here, in this direction is differentiation, deriving or differentiation. Going that way, coming back this way, anti-differentiation, or as we'll most likely call it, integration, or most often call it, it's integration. So when we are faced with 2x plus 2 and we want to integrate, we're going to get back to x squared plus 2x. So it's just the reverse process. How does it look then? So we have to learn some terminology. This means the derivative of this with respect to x. How would we write I want you to integrate 2x plus 2? So let's have a look at that. So this is how it looks. It's an elongated S, which actually refers to sum. We'll get into that when we start talking about areas and volumes and things. I'll talk a little bit more about why this symbol is used, but for the moment, just want to understand that that's saying, just like this is saying derive this, this is saying integrate this with respect to the variable x. So we need a little dx on the end there, just like we've got a dx here. So this is equal to, well, we've got the answer here, haven't we? X squared plus 2x. Okay, so that's going back the other way. This means integrate. That's in a symbol there means integrate 2x plus 2 with respect to x. That's what that whole thing means, in fact, no other than just that sign. That whole expression there means integrate 2x plus 2 with respect to x, and there's the result. That's the integral, or the integral of this, just as this is the derivative of this expression here. Okay, but I want to raise something with you here, because I'm going to go back to x squared plus 2x. I'm just going to maybe go on the side here. So if we wanted to derive x squared plus 2x plus 1, then we would still get 2x plus 2. So how do we know? So how do we know? So if we look at the derivative of x squared plus 2x plus 1 is 2x plus 2. So the integral of 2x plus 2, so therefore that would suggest, would it not? Therefore, the integral of 2x plus 2 with respect to x is equal to x squared plus 2x plus 1. But hang on a sec, over here we said the integral of 2x plus 2 dx was equal to x squared plus 2x. So, which is right, x squared plus 2x or x squared plus 2x plus 1? Well, in this case, there was no constant. As you know, when you have a constant, upon differentiation, it disappears. So when we have a function to integrate, we have to allow for the fact that in the original function, in the derivative, in the function that was derived, there was a constant that disappeared. So in fact, it would be correct to say, so therefore, we say that the derivative, the integral of 2x plus 2 with respect to x equals x squared plus 2x plus some constant c. So this is to allow for the constant that disappears upon differentiation. So we don't have any evidence of it. So we need to allow for it. Now that c could be 0, and most often, if we're just integrating, we just allow for the c. When we start to do some evaluating, we will see that we will accommodate c, we'll find a value for it, and we'll be able to proceed with the problem. For instance, for example, let's have a look at an example. I'll pause. So we're jumping ahead a little bit here, but just to give you, just to put this in context for you and give you an idea of how this constant gets allowed for, just have a look at an example from an area that we've looked at previously, and that is the motion of a particle in a straight line. So the velocity of a particle is given by this expression here. Velocity equals 2t plus 2, so t is in seconds, and v is dx to t, the derivative of, or ds to t, because we're considering s as the displacement, aren't we? So ds to t is 2t plus 2. So find its displacement after t seconds, after 6 seconds, if initially the particle is at the origin. So we want the displacement equation. So what we do is we'd integrate 2t plus 2. So we're going back. Now you remember, if you had a displacement equation, you derived it to get the velocity equation, and you derived again to get the acceleration equation. We've got the velocity, and we're going to go back to displacement. So if you remember, we went displacement to velocity to acceleration, and this was deriving. This is finding d dx, deriving d dx. Right, now going back the other way, which we're doing from velocity to displacement, we're integrating. That's a little integral sign. So that's what we're doing here. We're integrating 2t plus 2 with respect to t. So we find that is equal to, as we've been working, I'm just still working with my 2x plus 2, or 2t plus 2 in this case, is 2t squared plus 2t, allowing now for the constant c. So my displacement is t squared plus 2t plus c, initially meaning at t equal to 0. At t equal to 0, s is equal to 0. The particle is at the origin. So therefore, 0 equals 0 plus 0 plus c. So c is equal to 0. So we can now say with confidence that my equation, my displacement equation, is 2t plus 2. So therefore, at t equal to 6, s is equal to 14. So find its displacement. Its displacement is 14, so 14 units to the right of the origin after 6 seconds. There's an example of how integration is used to backtrack, given velocity or given acceleration, to work our way back. But every time we're going to have a constant when we go back, when we backtrack, when we integrate. We're going to have a constant that we need to explore. We need to find out what its value is, and we need to look for evidence of what its value is. Okay, so how do we integrate? So what we've looked at here is an example. I've integrated based on the fact that we're just using our knowledge that integration is anti-differentiation. It's the reverse process. So if I know how to differentiate x squared plus 2x, it goes to 2x plus 2. So therefore, the integral of 2x plus 2 must take me back to x squared plus 2x. But what's happening here? So let's have a look. Where on differentiation, we drop in power, don't we? And we multiply by the current index. So 2 comes down, we reduce the power by 1. So on integration, we go the opposite. We raise the power by 1, and we divide by the new power. So let's have a look at what would happen. So the integral of 2t plus 2, let's go back to x because we're more familiar with x, 2x plus 2 with respect to x. Okay, so let's see how we do that. Let's pretend now we haven't looked at how we don't know what it's don't know what the derivative, what we derive to get this. We're starting from scratch with 2x plus 2. So what we do is this. We look at 2x and we raise its power by 1. So currently it's got a power of 1. We're going to raise its power to 2. So we're going to go 2x squared. So the 1's gone to 2, and we're going to divide by that new power of 2. Okay, so we'll continue and we just deal with each term as we go, just like we did with differentiation. Now the 2, well, that's 2x to the 0, isn't it, currently? So we raise its power by 1, so it becomes 2x to the 1, and we divide by 1, plus a c on the end. Tidy this up, and we get x squared plus 2x plus c, which is what we've established up here. Okay, so let's have a look at another example. The integral of x to the power of 10 with respect to x. So we take our power and add 1 to it and divide by the new power. So our rule will look like this. The integral of x to the power of n with respect to x will be equal to x to the power of n plus 1, so we raise the power by 1, divide by the new power, and add c on the end. Okay, so a couple more examples, then we'll call it quits. If we're integrating 1 over x to the 5, so we've got to put it in integratable form first. So we'll write that as the integral of x to the minus 5 dx. Now it's in integratable form. We'll take it, we'll get rid of the integral sign, and we're going to integrate now. We're going to add 1 to the power, minus 4. We're going to divide by the new power, minus 4. So, and we're going to add a c on the end. So, okay, and perhaps we want to always watch our manners with our maths, and perhaps we want to write this in a little more acceptable form. So that would be minus 1/4 x to the minus 4, which is pretty good. Or we could improve it again by just writing it as minus 1 over 4x to the power of 4 plus c. But we're just window dressing at this stage. Let's just get the basics right here. So let's just do one more. If we're integrating, let's have a look at a square root or a cube root in this case. No, the fourth root. I'm just working from examples in the textbook, so you can refer to those as well. X to the power of 3. Okay, so put it in integratable form, so leave the integral sign there, tidy it up. That should say 3/4 there, dx. This is the root we're taking to the power. Now we're ready to integrate, so let's drop the integral sign, add 1 to the power. 3/4 plus 1 is 7/4. I just added 4/4 to that. I'm going to divide by 7/4. I'm going to add a c on the end. This needs tidying up. I'm going to multiply top and bottom by 4. So I'll get 4x to the power of 7 over 4 over 7 plus c. Alright, that's all good. So let's get some practice now on integrating exercise 9a, page 293. So we'll attack that next time I see you.